The concept of time travel has fascinated readers and movie buffs for a long time. While people are intrigued by it and hopeful it will become a reality, the truth is no one has been able to pull off this groundbreaking feat just yet. However, we do live in an era where science is advancing rapidly, constantly pushing the boundaries of what's possible. So, what do we know so far, and in theory, about what the physics of time travel might involve? In this video, we take a look at where we stand on the possibility of traveling through time. How time works. You might be surprised to know that how time works exactly is still a mystery to physicists. For now, traveling into the future seems possible, as we move toward it every day. But when it comes to potentially meeting our great-great-grandparents by traveling into the past, that seems extremely difficult, if not nearly impossible. Albert Einstein was key to our current understanding of time travel. His theory of relativity provided a framework for space, time, mass, and gravity. Theory of relativity. For Einstein, time was relative. One key result of relativity is that the flow of time isn't constant. Time can speed up or slow down, depending on the circumstances. The fact that time can speed up or slow down is where the idea of time travel as a possibility comes in, with real-world implications. Time passes faster, but to notice this effect, you'd have to travel at the speed of light. Similarly, time passes more slowly in a strong gravitational field, like near a black hole. The Earth's gravitational pull is stronger at your feet, so your feet are actually aging more slowly than your head. GPS satellites. For us, day-to-day, the relativistic effects on time are too subtle to notice. But they do affect satellites used in the Global Positioning System, GPS. Clocks in the sky run faster than clocks on Earth. Because of this, they need to be constantly adjusted to ensure accuracy. Otherwise, your map app could be off by as much as 10 kilometers a day. Traveling to the future. Relativity means it's possible to travel into the future. Whether traveling at the speed of light or spending time in a strong gravitational field, you would experience a relatively short subjective time. In contrast, decades or centuries would pass in the rest of the universe. So when you return, you'd be far into the future compared to the time you left. Relativity opens a few doors for time travel, but so far it hasn't advanced beyond the theoretical stage. Closed time-like curves. A study published in 1949 by Kurt Gödel proposed that a closed time-like curve, a path where space and time loop back on themselves, could make time travel possible. However, a major problem with this theory is that no closed loops exist anywhere in the universe. It's pure theory. Without evidence of a closed loop, there's no way to recreate one. Emily Adlam, a philosopher at Chapman University in California, says, "Even if we had far more technological power than we do now, it seems unlikely that we could intentionally create closed time-like curves. Cosmic strings." In 1991, physicist Richard Gott proposed that such a closed loop might be possible if there were two cosmic strings moving past each other in opposite directions. That would be great if cosmic strings actually existed. These strings are still hypothetical, though, and some theories suggest they could have formed the early universe. Wormholes. Another phenomenon that relativity seems to allow is wormholes. In theory, space-time could be bent like a sheet of paper, allowing a tunnel to be drilled through it, creating a shortcut between two widely separated points, also known as a wormhole. Again, the problem with wormholes is that while it's been shown theoretically that they could exist, whether they physically exist is a completely different matter. If wormholes did exist, they wouldn't last very long. In fact, if they're formed by two black holes coming together, as theorized, their intense gravitational field would cause them to collapse under their own gravity. Here's more bad news for would-be time travelers. These wormholes would be microscopically tiny, too small for even a bacterium to pass through, let alone a human. Negative energy. To solve the size and gravity issues, a massive amount of negative energy would be needed inside an atom. The energy of the atomic field generally needs to have more positive energy, so even if small pockets of negative energy expanded within it, this isn't exactly a realistic proposal. Quantum mechanics. While relativity describes the behavior of large objects like humans and galaxies, quantum mechanics explains the behavior of the very small, smaller than atoms, such as electrons and photons. Strange observations have come from quantum mechanics, notably non-locality. This is where a change in the state of one particle in one location can instantly influence another entangled particle somewhere else. Einstein called this spooky action at a distance. This theory has been experimentally demonstrated many times, but many physicists are still unsatisfied with the possibility of non-locality. That's because for the effect to be instantaneous, information would have to travel faster than the speed of light. And that should be impossible. Retrocausality. In response, some physicists have come up with an alternative way to interpret these experiments. Some propose that when something seems instantaneous, it actually traveled to the future and came back. This introduces the theory of retrocausality, events that occur in the future and affect the past. If this is the case, our linear concept of time might not be entirely correct. In fact, it means that information from the future is always looping back to influence the past. Keep in mind that this theory isn't universally accepted, and some find it even more outrageous than non-locality. Conclusion. In conclusion, we don't have a full answer yet. Relativity and quantum physics don't exactly mesh well with each other, but they do help explain certain aspects of our universe. Maybe there's a unified theory that ties them together, but it hasn't been discovered yet. For now, time travel remains out of reach, just like the most mysterious workings of the universe. Even with all the fascinating theories out there, time travel is still stuck in the realm of science fiction. Physics gives us some clues, sure, but our tech just isn't there yet. For now, time travel remains more of a cosmic mystery than something we can actually pull off. So yeah, for now, time travel is still just a theory. But hey, who knows what the future holds, right? Science keeps pushing forward, and every discovery gets us a little closer to making the impossible possible. If you enjoyed this video and want more mind-blowing topics like this, don't forget to hit that subscribe button. And of course, give it a thumbs up to help the channel grow.